All right, we are going to go ahead and get on our 9-3 notes. So we are going to be talking about geometric means and how they're related to altitudes. The first theorem that you need to know is called the right triangle similarity theorem. So it says if the altitude is drawn from the hypotenuse of the right triangle, then two triangles formed are similar to the original triangle. So remember, altitude is from one vertex of a triangle to the opposite side that meets that side at a right angle. So the picture shows pretty clearly that the original triangle, AC or ABC, can be split up into another two small triangles when they draw that that altitude, and all three of those triangles, the original, the red triangle in this case, and the blue triangle, are all similar triangles. So example 1 just says identify the similar triangles in the diagram, so it's pretty straightforward. I'll just do, we have the original triangle, which is MPQ. So triangle MPQ, and then we have triangle QMN, and I don't know, sorry if I might not be putting these in the right letter order. QMN, and then we also have just this side. Oops, I should have done it with the highlighter. It's okay though, you get the idea. NPQ. So those are the three triangles, and those are all similar to each other. Okay. Example 2 says a roof has a cross section that is a right triangle. The diagram shows the approximate dimensions of the section. Find the height of the roof. So in this one, we're finding the value of the altitude. So we have a couple different triangles there, right? We have this small triangle here, which we only know we know the hypotenuse is 25, but we don't know the legs. We have this triangle in blue, which we know the hypotenuse, but not the legs necessarily. And then we have the original triangle in this yellow, and we know the legs and the hypotenuse of that. So if I need to find the value of h, which in this case, there's a couple ways to do this. So I'm going to use the smallest triangle, the SRW, and H is the longer leg. I'm just going to put long leg, and then 25 is the hypotenuse. That's going to equal the long leg of my largest triangle, which is RST, where the longest leg is 60, this side right here, and then the hypotenuse is 65. And once we have this, we can just cross multiply and divide. Sorry, I'm just pulling out my calculator. So we would do 25 times 60 is 1,500 divided by 65 equals about 23.08 would be our answer. If you do it a different way, it should end up the same. So if I use the longer side, no, I'm not going to do it a short way. I'm not going to do it a different way. But it's really important that you make sure you line up, like the 25 and the 65 are both the hypotenuse, hypoteni, I don't know if that's a word, and then H on the smallest triangle, the altitude, is the longest leg, and then on the biggest triangle, 60 is the longest leg, so we have to make sure we line those up. Okay. A geometric mean. A geometric mean of two positive numbers, a and b, is the positive number that satisfies a over x equals x over b, so that x squared equals a times b, and x is the square root of a times b. So this is going to come into handy. So if you were given two numbers, they said, and they asked you what the geometric mean was of 8. Oh, we're going to do one actually. So let's just go to the next page. So it says find the geometric mean of 8 and 10. So we're going to do 8 over x equals x over 10. So if we just cross multiply, we'd end up with x squared equals 80. And then we take the square root of both sides, and we're going to want to simplify this with the square roots. I know this was a little bit tricky for some people. So x would equal, let's see, the square root of 80. We could rewrite this as the square root of 4 times 20. and I know the square root of 4 is just 2, so I'm going to pull a 2 out. X equals 2 to the square root of 20. But I also know that I could pull another 4 out of 20, and I pull a square root of 4 out of here. I'd be like x equals 2 times 2 now, times, it'd be left over with the square root of 5. So x equals 4 square root of 5. Okay. So it says from the right triangle similarity theorem, you know that that was the first theorem, that one triangle with the altitude drawn from the right angled side creates 2 more similar triangles. Because the triangles are similar, you can write and simplify the following proportions involving geometric means. So that's why we just learned about geometric means, because they're going to be in the next 2 theorems. Really quick, this is supposed to be an equal. I don't know why it got cut off. So this is an equal sign. So the first one says, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. Obviously, right? The length of the altitude is the geometric mean of the lengths of the 2 segments of the hypotenuse. So we can use these 2 lengths here. Oh, let me use a highlighter. This red length AD times this blue length BD is going to equal, that's going to be the altitude is going to be the geometric mean of those 2 lengths. So what we just did with the problem above, we could do to figure out the height of this triangle. Excuse me. Okay. Now the geometric mean leg theorem says that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments, obviously. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Whoa. It's okay, we have some formulas here. So this tells us that the hypotenuse CB is the geometric mean of DB and AB. So CB is the geometric mean of this length and this length. Okay? And AC squared is going to equal, or it's the geometric mean of, I'm running out of colors here. Here, I'll use pens. So this length squared is going to equal this length times AD times AB, the entire length. So if you look at the one I just drew, these 2, AD over, these 2 are segments of this hypotenuse, and AC is the longer leg, and the other one, CB, is the shorter leg, and these are the parts of the hypotenuse. Okay, this is confusing. However, you get to use these on a test or quiz. So you don't need to memorize it, we just need to know how to use it. Here we go. Okay. It says find the value of each variable. So we're going to use that first. I just took a picture of that. Sorry, I'm going to pull it up on my phone because I don't want to have to go back to the slide when we're doing this. So we're going to use that geometric mean theorem, which tells us that the altitude is going to be the altitude squared. So this, I'm just taking this right off of that first theorem from the last page, theorem 9.7. X squared is going to equal this length times this length. So my altitude is going to equal 10 times 4. So my altitude is going to equal 40. And then if I pull out a perfect square, I know that x squared would be equal to the square root of 4 times 10. I think that's going to be it. We know the square root of 4 is just 2. So, oh, sorry, I took the square root of both sides. So x equals 2 times the square root of 10. And there's not another perfect square in there, so we're just going to leave that as 2 square root of 10. Okay. This one we're finding the value of each variable. So this one we're gonna find y. So I'm gonna look at the theorem 9.8. I'm looking at it. You would want to go back and look at it. So the first one says that I'm going to replace the letters with the values that I see. So the first one that was drawn is CB squared equals DB times AB. We're going to use the top of the two that were listed in the theorem. So CB in this case is going to equal y. So y squared equals DB, which is the short segment 3, and AB was the entire segment, so this would be 11, because I'm adding the 3 and the 8. So y squared equals 33, which means y just equals the square root of 33, and 33 can't be broken down into any perfect square, so that's our answer. Again, if that seems confusing, I would absolutely have this theorem out when I'm doing my work. So whether you split screen it and have it up, or you write it down on a piece of paper, or you do your work on paper and then go back and put it into big ideas. But these are not, to me, these aren't super intuitive. It's more of a technical math thing where you're going to want to have it in front of you to use as a tool. Okay. The vertical distance from the ground to your eye is 3.4 feet. So we're doing a word problem here. The vertical distance from the ground to your eye is 3.4 feet, and the distance from you to the gym wall is 8.1 feet. Approximate the height of the gym wall. So again, this is a triangle, so the altitude here is 8.5 feet. And I have two parts of the base of, the hypotenuse. So I'm going to flip this over so it looks like this. This is what the triangle looks like when I'm looking at this. That's how my brain pictures it. So this height is 8.5, this is 5, this is W. So right away I notice that I can use the geometric mean theorem for the altitude, because I have the altitude and I'm missing just a part of that large hypotenuse for the biggest triangle. So that was theorem 9.7. And again, I'm looking at this on my phone, so it's definitely okay to look at the theorems when you're looking at the problem and figure out what you need to use as a tool, right? So this tells us that the altitude squared, so 8.5 squared, and I apologize, it's really sloppy because I lost my pencil, I'm so sad, equals AD times BD, or the two segments of that hypotenuse, so 5W. So then we're going to figure out what 8.5 times 8.5 is. 8.5 times 8.5 is 72.25. 72.25 equals 5W. And then we'll divide by 5, and we're left with W equals 14.45. But it says approximate the height of the gym wall. So we're not quite done, because we need to know this total value. So we would add 5 to that. So the height is 19.45 feet. Oh, is this all this there is? I think we're done. Okay, so that's all I have for you. Again, use those theorems, have them out to picture the triangle and what are the segments you're trying to find and what segments are given to you, because that is going to be key in figuring out which theorem is appropriate to use for which problem.